Okay. Welcome everybody. Today I'd like to talk about how we characterize dust and carbon in the epoch of reionization. And I've really enjoyed the question sessions inside the Slack previous couple of days. So I would like to suggest everybody who has questions to please just throw them onto the Slack. And if I go too fast in this presentation, please find these slides on my website. And the link is given there. So I'd like to talk about the dust budget crisis that we're experiencing, where high redshift Lyman-Break galaxies appear to have more dust than is able to be produced by supernovae and other phenomena. So this is actually quite surprising because initially we weren't quite so convinced, as for example, Jorge Zavalas showed yesterday, that that dust played a major contribution in the high redshift universe. So, however, here I would like to use a single galaxy, a high redshift Lyman-Break galaxy, and show how we used ALMA to characterize both its spectral lines and its spectrum to look at both this dust production and to hopefully provide a solution to this problem. So first I will talk about the source. I will talk about how the spectral lines are able to characterize the metallicity and different properties of the source, and how the dust continuum is a very important probe for future follow-up. So MAX 0416Y1 is a Y-band dropout behind the Hubble frontier field MAX Y1. So this Lyman-Break galaxy is detected, and we can see the spectrum on the left-hand side, where we see the redshift at redshift 8. It looks at around, or it is about 2 kiloparsec in size by 1 kiloparsec, and it looks like it's composed of multiple components. And provided by Tamuya 2019, they executed an oxygen redshift search, and they find the redshift at 8.3. They also detect the dust continuum at 850 micron, and the oxygen is well detected. Using UV-to-FIR infrared modeling, we can find stellar mass and star formation rate that agrees with models of galaxy formation of a young stellar population. However, this young stellar population cannot account for the high metallicity we find of these sources. Neither can it account for the dust mass we find, further suggesting a dust budget crisis. But this suggests that there exists an older stellar component at redshift 15. So yesterday's talk by Robert Sporsani further exemplified this, and the power of ALMA in these situations to probe older stellar components and older production mechanisms. So together with the oxygen, it drove us to look for a C2 emission of this galaxy, another very bright spectral line. And unlike previous sources, we find that the spatial positioning of these sources is similar in both spatial positions and in velocity space. The oxygen and the carbon are coming from seemingly similar positions. This is strange because C2 is more associated with atomic or with neutral gas, while oxygen 3 is mostly only found close to very strong UV radiation sources. So when we compare the luminosity, as I'm sure we'll talk later about Hagikane, but also a poster by Hagimoto, which should be on the Slack soon, we find that the ratio between the oxygen and the carbon emission of this galaxy is significantly higher than is seen in local galaxies. Only in dwarf galaxies do we see ratios this high, and we find this ratio to be common among high redshift galaxies. Part of the explanation was maybe offered by Carniani 2020, who showed that the C2 emission is more extended and therefore more often missed. So we correct for this in the leftmost source. Our source is the orange bright spot in the center, and we see that it has a very high oxygen over carbon ratio. This suggests very strong radiation fields or many other properties to do with the galaxy evolution. Now, if we continue to look at the C2 luminosity versus star formation rate, we find that it falls below the typical Delosa relationship. So the source does not fall on the Low's relationship, and it actually falls among a bunch of Lyman alpha emitters and not among Lyman-Break Galaxies between redshift 5 and 7. Instead, our source at redshift 8 falls among Lyman alpha emitters, and this could be because the differentiation between these two sources fades as soon as the medium in which it resides is mostly neutral. Indeed, it agrees with the Lagache model, which takes into account PDR development at very high redshift. Our spectral line was bright enough that we were able to differentiate a velocity gradient across this source across this source, which is suggestive of rotation. This was previously also seen by Smith, 2018, into high redshift Lyman-Break Galaxies, and I'm looking forward to seeing the results from the Alpine survey tomorrow. The velocity of the line width compared to the velocity gradient is suggestive of rotation, but it could also be suggestive of an outflow. And this was demonstrated nicely in Fujimoto 2019, who showed that there exists a wide distribution of C2 emissions. And similarly, in the Alpine, the most star-forming Alpine sources, we see that there exists C2 emission at very large velocities. However, this is also suggested by galaxy models, such as Arata 2019, which suggests a sort of pulsating galaxy evolution at high redshift. So here we see that it's very important to have both the kinematics that ALMA is able to give and directly compare it to models. Now, if we just take a back of the envelope calculation, and we put a little postage stamp onto this source, we can calculate that the mass loading factor, so the amount of outflow versus star formation rate, is on the order of 0.1 to 100, meaning that if indeed this is an outflow, then outflows are significant in the early evolution of galaxies. I'm looking both to the talk later today, and I'm looking forward to the talk of Fujimoto tomorrow. Now, we failed to detect continuum emission around the C2 spectral line, while we did detect 88 micron continuum emission. And this puts a very strong upper bound on the spectrum of this source. As such, we expect this source to be significantly high in temperature. And part of the reason that this is important is because such high dust temperatures mean that the dust mass, on average, is lower. This has also been suggested by galaxy evolution models, such as Palatini 2019, where they show that a lot of the dust exists at relatively cold temperatures, but the predominant dust that is seen exists at high temperatures. So the dust, the luminosity weighted dust mass is indeed very high. Part of the reason this is a problem is because we look at these galaxies not just at continuum, but we're looking at spectral lines. So we're looking at oxygen 3 lines, or we're looking at C2 lines. And typically in the local universe, these fall around the positions you're able to characterize the SED. However, at the high redshift universe, this could be that we're missing out this information because it's both very difficult to probe short rest frame wavelengths, and at the same time, not looking at a spectral line is harder to justify. Just because the amount of dust mass is lower does not mean that the dust is less luminous. It could, in fact, be that dust plays a more important role than we previously assumed, but it would solve the problem of the dust budget crisis. So maybe I went a bit quickly here, but I hope I've shown that Lyman-Break galaxies are very important probes of early galaxy evolution. And with these sources, and especially using ALMA on these sources, we're able to target spectral lines that are able to characterize the ISM of these sources and look at the morphology or the kinematics of them. Personally, what I find very interesting is the spectrum and the dust emission of these sources. And I'm looking very much forward to using galaxy evolution models on dust production, and thus trying to constrain stellar populations. I'm looking forward to your questions. Thanks.
Thank you very much, Tom. We have a couple of questions. Seiji Fujimoto asks, do you find any difference in the kinematic structures between the C2 and the O3 lines?
Unfortunately, the O3 line was not observed significantly enough to see velocity structure. Or when we looked at the moment, the first moment map, we did not see any velocity gradient.
How much deeper do you think that data would need to be to extract any O3 kinematic?
Yeah, so our oxygen line detection was around a sigma of 8, while C2 was at 11 or 12. So it wouldn't have to be that much further. It could be an interesting pursuit, I agree.
Okay, thanks. We also have a question on what's the stellar mass of the redshift 15 stellar population?
This would be, I think, a factor of 10 higher. So allow me to switch through my slides real quick. Hope you can flip out. Okay, so I think we find a young stellar population of 10 to the power 8 around that. I think the older stellar population would be 10 to the power 9. However, it wouldn't interfere with the Hubble emission very much.
Okay, one more question. Can you place lower limits on the dust temperature?
I should have said this, of course, but indeed, we've placed lower limits on the dust temperature of around 80 Kelvin.
I think we can squeeze in one more. Jorge Zavala asks, was the 850 micron dust continuum measurement corrected by the line contamination?
Sorry, can you repeat that question once more?
Oh, sorry. Was the 850 micron dust continuum measurement corrected for line contamination?
Yeah, exactly. This is line subtracted dust continuum.